over to me, but I could speak as long as I want. So he's not even going to try to give me time updates. So
you don't need a copy of
it. That's a joke, don't worry. So I'm going to move this down a bit. Yeah, okay. Good. So this talk is about lossy compression. And I'm hoping to speak to both what machine learning can provide to information theory in terms of new schemes and new architectures and so on, and also perhaps what information theory can provide machine learning in terms of performance bounds and crisp optimality results and so on. So this is joint work with Sara Bandani, who's a PhD student at Cornell, who's graduating next month, and Johannes Bale, who's at Google Research. All right, so let me begin by just describing the classical story about lossy compression from information theory. So this is sort of a folklore result. It's probably familiar to most people here, but let me go through it kind of quickly for good measure. So if you open up a textbook in information theory and read up on how to compress a source subject to a mean squared error distortion constraint, it'll say to do the following. So you take, okay, assuming your source is like a 1D time series. Okay, so you take your source, you divide it into chunks of size j, so blocks of size j, and then you apply a linear decorrelating transform to it, so the Cohen-Lev transform or some fast kind of approximation thereof. You get the transform coefficients, and then you quantize these. So EC dq stands for entropy constrained dithered quantization. So at a high level, you just think about taking each transform coefficient and then quantizing it according to a uniform quantizer. You get these quantized coefficients. These are discrete random variables now. You pump it all through your favorite, universal lossless compression algorithm, and those are your bits. And that's the compressed representation. And then at the decoder side, you just kind of undo this as best you can. So get the reconstructed transform coefficients or the quantized transform coefficients, and then invert the transform, and there you are. So this has an optimality result behind it, this kind of overall architecture. So it's within a quarter bit of optimal if the source is stationary and Gaussian, which is kind of a big if, but at least it has that result. It's also an asymptotic result, so low distortion. Okay, so high rate, stationary Gaussian, mean squared error. This architecture is provably near optimal within a quarter bit, and it forms the framework within which all the kind of standard compression standards that we know and love for music and video are formed. So JPEG and MP3 and AAC and VPC and everything, they're all formed from this basic architecture with tweaks to make it work all the better. Okay, so this was sort of like the state of the art from maybe about mid 70s when the final pieces were put in place in this story until about 2015, and then like many other areas, deep neural networks just kind of blew this area wide open. So here's just one performance plot. This one's a bit dated. It's from a number of years ago, but it gives you a sense of what's going on. So these are just simple rate distortion curves, SNR versus bits. This is for the Kodak data set. So there's JPEG, JPEG 2000. Those represent like the culmination, of like decades of optimization of this architecture. And so here's their curves, the dark, the black and black hashed. And in comparison, here are two neural network based compressors for the Kodak data set that are already handily beating it. And again, the JPEG are like thoroughly optimized. This is like the first and second cut, if you will, of the deep neural network approach. And it's already doing significantly better. So what's the difference? So what are neural networks bringing to the table? So, well, first of all, there are various approaches for using deep neural networks for lossy compression of images and music and so on. I'm going to focus on one particular approach that's sometimes called nonlinear transform coding. That approach adheres quite closely to the classical architecture. On some level, we just replace the linear transform with a nonlinear transform. Okay, so the linear KLT, the DCT gets replaced with a neural network. And of course, it's trained. Okay, so the linear transform was formed, mathematically from some model. These transforms are now trained, kind of end to end. But at a high level, it's like what was a linear transform is now nonlinear, and that's the tweak, that's the change. All right, and for images, this beats linear transforms, as we saw in the previous slide. even under mean squared error. Okay, so the real power of this method is that you don't have to use mean squared error, right? Like any distortion measure you can differentiate. Okay, you can optimize for. So you can use metrics that capture human perceived distortion much better than mean squared error does. But even on the home turf of the classical method, okay, this is still beating the classical method, the classical architecture. Okay, so what can we take away from the story so far? Evidently, images are not stationary Gaussian processes. Like, this is not a big surprise to people, but this like seals it, right? Because if they were, then like nonlinear methods should really buy us nothing per the theorem, and they're buying us something. So that's the end of that. And as such, like the theory that's based on that assumption is also kind of out the window, right? I mean, the classical theory says you shouldn't need nonlinear methods, and yet we do. So it's like that classical theory is not, evidently so useful anymore.
I think it's a fair comparison because the neural network is trained for. Of course, we have transformers now, but nonetheless, it's trained for a data set, however large it is. And these are generalized transforms for any data set. Of course, you have to tune the Huffman coding tables for appropriately, but I don't think it's a fair comparison.
So what are you comparing?
Like just as you compared, you said JPEG and MPEG or whatever. I mean, they're not.
Yes.
That's why we improved with ANNs.
Yes.
Yeah, so
Yeah, I
it's
mean, there
also tuned to that code, that data.
Sure. Yes, they are. I mean, JPEG does have a wider region of robustness, I think, than neural networks. That's true. But it's not like it only works for like faces or something.
You could also you could have learned you could use PCA and empirical KLT, just like that, right? So I think it's a fair comparison.
Oh, yeah, okay.
For KLT, like I said, you could learn the covariance structure from data.
Yeah, so there are two distinctions, right? There's the training and there's the nonlinearity.
Yeah.
And I agree. I'm sweeping the training part under the rug and I'm focused on the nonlinearity. But I agree with you. I am sweeping something under the rug.
Sieve, right? He says you don't need to know the model. It's the universal rate distortion coding up to a quarter bit. Whereas the transform part also takes that, but combines it with some source modeling.
Yeah, so I think what he's saying is that the transform needs to be nonlinear. That's his point. Right?
That's the point here.
So sorry, I'll let you take it.
Yes. Okay. All right. So, I would posit that the classical theory, at least as I put up there, is not so useful moving forward, and that it indicates that the nonlinear transforms are not useful, and evidently they are. So we'd like to develop a new theory to kind of replace the old, one that can do all the things we want of a theory. So explain why things that work well in practice work well in practice, quantify their gap from optimality, and maybe show how they can be improved. So, usual value that information theory provides us, we'd like to obtain that. And I do not have a grand new theory of rate distortion to provide you here. I have two kind of toy models. These are both source models that, although they're simple, do actually speak to all three of these points, as we'll see. So there's two of them. We call them the Sawbridge and the ramp, and they do speak to all three, and I think moreover they're toy models. They're stylized, but they do capture certain properties of images. So they both have homogeneous regions separated by an abrupt edge, and the edge is kind of randomly placed, and they also capture this idea of like low dimensional structure and high dimensional space, the so-called manifold hypothesis for images. Okay, so I'm going to talk about each of them. I'll do the Sawbridge and then the ramp. All right, let's do the Sawbridge first. So it's a continuous time random process over 0, 1. It's quite simple. So it's just x of t equals t with a random unit drop, at a random time, a uniformly distributed time over 0, 1. Okay, so a typical realization would look like this. Okay, so it's just x of t equals t, except that there's a unit drop at a random time u. That's the process. Okay, so it's like an image, right? That's like a 1D image, right? You have these like two textures and then there's a edge between them, right? Okay, so we did not invent this process. Okay, we learned about it from this very nice survey paper by Donahoe et al. They call it the ramp. We call it the Sawbridge, both because we think it's a more descriptive name for this process. It's a bridge, right? It starts and finishes at the same time. And also we want to use the word ramp for another process that comes later in the talk. So we're going to change the name. They credit Meyer 92 I can tell you, I pulled up the Meyer 92 paper myself. I read it start to finish. I cannot find any reference to a process that resembles this at all. So I'm not, probably Meyer deserves credit, but maybe not the paper they cite. In any event, it's not our creation, but it's a great example to study, in part because like you want to talk about low dimensional structure in high dimensional space, like this has the maximum possible discrepancy between the two. Okay, it's a one-dimensional process. It's completely described by the U. Okay, and yet the energy is spread over infinitely many dimensions. Okay, any finite dimensional subspace is not going to capture all the energy of the process. Okay, so like infinite dimensional space with like a one-dimensional spline in it. And that's the process. Okay, so this is talk about compression. So how well can we compress this process? So here's the formulation we'll use. So an encoder is a map from function space to some discrete set. And we're going to look at the trade-off between the entropy and the mean squared error. So an encoder is just a map from the function space to a discrete set, like I said. And we want to minimize the entropy of the output of the encoder subject to a mean squared error constraint. This is not the only way of formulating it, of course. This is one shot. So compare with the rate distortion function where you get like, many realizations of a Gaussian source. Here, you get one Sawbridge realization. You compress that. That's it. There are many copies of this thing. The Sawbridge is your image. Okay, it doesn't represent like one pixel. It's like the whole image. Entropy, of course, approximates the expected coward length. And this is actually what the ANN compressors that we've been looking at are optimized for. They try to minimize the entropy, discrete entropy at the output of the encoder subject to, say, a mean squared error distortion constraint. So if we want to, compare these curves that you get from this this definition against, actual plots from neural networks, it makes sense to, look at what they're trying to optimize, which is this. Okay, so this process is simple enough that you can actually compute h of delta exactly. It's implicit, but it is exact. So the power in the process is a sixth. So mean squared error above that, the rate required is 0. For anything less than that, you can compute it, implicitly in terms of these formulas. At a very high level, you basically want to like quantize U. Can I go back? Like the process is completely described by the location of the drop, right? So just intuitively, like the encoder should just like identify where U is, quantize that, tell the decoder the location of U within some quantization error, and then the decoder just creates an MMSE estimate of the whole function given that information. So the proof here just amounts to showing that like give me any encoder, I can dominate it by one that quantizes U using contiguous cells. You then have to optimize the cell sizes. This is a non-convex optimization problem. It turns out to be kind of non-trivial, but it's actually equivalent to a quantization problem solved in a different context in this paper. And so that's what gives you this characterization. All right, so this is a bit messy. It's useful to look at asymptotics. So as the rate goes to infinity, or equivalently the distortion goes to 0, the rate blows up as 1 over the log 1 over the distortion, which may be a touch surprising. You might expect a half here because it's like a 1 parameter process, but there's actually not a half there. That's maybe a topic for another talk, why that happens. Anyway, log 1 over delta is the main takeaway. You can look at how well the classical architecture compresses this, and the answer is very poorly. Okay, so first you work out the KLT for this process. This process has the same autocorrelation and hence the same KLT as the Brownian bridge. So, if you can open up more textbooks and kind of write down the orthonormal basis and stuff, the real contribution of our theorem here, just to point out that like the coefficients in the KLT can be expressed quite simply in terms of that U variable that describes the process, which is useful because now we can talk about the entropy of just like quantized versions of Y, and then plot that and compare that against optimality. Okay, so if you consider the entropy of like the classical architecture, so KLT coefficients, you water fill, you entropy code them, you get an entropy for a given distortion. As the distortion goes to 0, that entropy blows up as 1 over delta. So it is exponentially suboptimal. Right? The right answer is log 1 over delta. This is 1 over delta without the log. Okay. Essentially because it's a linear transform, it can't extract the U. Okay, so it has to like project into all these different dimensions and then like, try to describe all of these like uncorrelated random variables that are of course highly dependent with each other. There's one U that controls them all, right? So you don't really need all these bits. Yeah, the entropy blows up as constant divided by delta. We can describe the constant, it's a big mess. It's like a convolution, entropy of a convolution of arc sign density and so on, but you can compute it numerically, 0.3. Okay, so how well do neural networks do? So it's not hard, by the way, to write down by hand a shallow neural network that compresses this thing optimally. Okay, so the question is not like, is there a neural network that compresses this thing well? The question is, can like stochastic training find it? Okay, and if you take like off-the-shelf neural network compressors for images and just train them on this instead, like, how well do they do? So we took the off-the-shelf state-of-the-art neural network compressor for images and trained it on a bunch of Sawbridge realizations. And all the details are here. You got to quantize or discretize the process, sample the process in time, of course. It has to work with a vector, not a continuous time process. These are all the details. I won't spend too much time on these. Maybe I'll just point out that like there is for people who aren't familiar with this particular application of neural networks, there's a complication here in that like to do lossy compression, you got to quantize to get bits. Quantizers, like a pure quantizer has a zero derivative almost everywhere, right? So if you have like a straight quantizer in the middle here, you cannot back propagate through this and get anything useful out of it. So you need some kind of workaround for that. There are various workarounds that people have used. You can do dither. So you minimize like some proxy for the rate plus lambda times the distortion with like, a dither variable that kind of softens the edge of the quantizer. The state-of-the-art approach is actually to start with that, and then over the course of the training, like anneal to a hard quantization. So you kind of move from this to this over the course of training. You got to get the kind of the quenching schedule right and stuff. But anyway, this is Augustin Bayes' approach, which works best. Okay, so numerical results for the Sawbridge. So this is the optimal curve just from the theorem. So SNR versus rate, log 1 over delta. So it's linear on a semi-log scale. And we train the neural network on this, just giving it Sawbridge realizations to train on, and then plotted its performance. And it is spot on. Okay, it's not order optimal or like within a constant. I mean, it's just right on the curve. So it nails it. We also force the neural network to use a KLT. Okay, so we kind of lock the transforms to be a KLT, but we allow it to do like water filling, gain optimization, and we compute the performance experimentally like we did for here. And you see it's exponentially suboptimal. You can plot a theory curve here too, and it's more or less the same. We don't show the theory curve. If you take the neural network and remove the nonlinear activations, but allow it to optimize the transform, so find the best linear transform, that does quite a bit better, actually, but still quite suboptimal. So KLT is not the best transform with this example. You can also lock the neural network to use, whatever you want, like a DCT or a certain wavelet or whatever, and like none of those really seem to buy you anything. They're just giving you the KLT performance back, which is interesting because the Donahoe et al. Paper I mentioned earlier. So they introduce I shouldn't say they introduce because I guess the process goes back to Meyer, but they talk about this Sawbridge process as a vehicle for understanding why wavelets work so well as the correlating transform. So the paper was written in the 90s when wavelets were, the emerging technology. And yeah, we find actually that wavelets don't really help much at all, but nonlinear approaches just blow everything else out of the water. Okay, so that's the Sawbridge part. So the Sawbridge, simple as it is, can explain the success of nonlinear transforms. It does quantify their gap from optimality, 0. Given that it's 0, they don't speak to how to improve the network because there's nothing to improve. But that takes us to the ramp. So let's move on to the second example. So just a tweak to the process. Okay, very similar process, but not exactly the same. So this process is x of t equals t minus half with a random cyclic shift to it. Okay, so just, x of t equals t minus a half, and then just apply a random cyclic shift to the whole thing. So, it's a typical realization. Again, a 1D manifold in function space. This one's a circle, however. Okay, and that like U realizations that are close to 1 and U realizations that are close to 0 give you a function realization that's very close to each other. Okay, so the Sawbridge does not have that property. It was kind of like a spline. This is really like a circle in function space, and we'll see that's significant for compression purposes. Okay, so we can run through the whole program. You can characterize the optimal compressor for this. Again, it's to identify the location of a drop and send that to the decoder. Now we cannot solve the optimization problem over the cell sizes for the U quantizer in closed form. So we just write it as this optimization problem over this. These are the cell sizes basically. You know, they sum to 1, they're not negative. This is their entropy. This is the distortion they give you. So I guess this is not computable in its current form, or it's not evidently computable, but using Lagrange duality, you can get a computable lower bound. That's quite good. So we plot this. We also train the neural networks on the ramp instead of the Sawbridge, and this is what we get. So this is a bit fine. I don't know how well this you can see from where you are, but so there's the black curve, the black solid curve, the black dotted curve. So the black dotted curve is our lower bound from here. The black solid curve is the upper bound we get by just choosing PIs that we like in this problem. Okay, so the optimum performance is between those two curves. They don't match, but you know, good luck trying to thread a needle, you know, through there, especially up in here. They don't match, but you know, they're almost on top of one another. And then you train the neural network with different values of lambda. This Lagrange multiplier that trades off the distortion versus the rate, and this is what you get. So it's fine at low SNR, and then at high SNR, it peels off. So it's suboptimal at high SNR, although it's on the curve at low SNR. So what's going on? So I have an explanation. It's a bit of an oversimplification, okay, but it's better than nothing. So I want to poke holes in part of the talk, like this would be the part of the talk to poke holes in, because this is not quite accurate, but it gets the basic idea across. So let's think about the whole process end to end. Like imagine, you know, nature picks the phase U, and then you generate the ramp realization that goes to the encoder, and then you compress, goes to the decoder, and you get something out. Okay, so what we'd like to have happen is for the encoder to extract the U, like the phase of the thing, because that completely describes the process, and it's like 1D, it's simple, it's uniform, right? And then you quantize that, and then the decoder would get a quantized U, and then reconstruct this thing as best it can from imperfect knowledge of U. And in fact, the encoder, you know, it seems like the encoder would have the harder problem, right? It's got to like extract this 1D variable from this thing, and the decoder would have an easier job. In fact, it's the opposite. The encoder extracts U no problem when we train it. The problem is at the decoder. So to see this, think about the mapping from U to like the process evaluated at one coordinate. You can actually think about it over here, right? So just like, you know, evaluate the process at one particular time, and now vary U and think about how the process varies at one particular time. So it looks like this. That's this map, right? As you vary U, this is how the process looks at one particular time slice. Okay, so it's decreasing in U until it jumps up by 1 and then decreases again. So that's kind of the map you want to have from here to here. And when we train it, however, we get is this. So the key difference being that we've got like these points here. So it's like it's not steep enough on the way up. It kind of catches some of the intermediate values on the way up. You know, at a very high level, it's like you want the decoder to implement this discontinuous function, and like it's a continuous function. In fact, it's differentiable. So like it's kind of limited in terms of how steep it can be here. And that's the problem. So this explains why this only crops up at low SNR. At high SNR, excuse me. At low SNR, it's fine. High SNR, we have a problem. Okay, and the reason is like this phenomenon is always present. But at low SNR, the distortion you pick up from this is sort of buried by the noise that you get from just quantizing U coarsely. But at high SNR, you're quantizing U very finely. And so the little bit of like indeterminacy you have here dominates your distortion. Like if the decoder gets, okay, I can't describe what I was about to say in terms of this plot. But anyway, there's some indeterminacy here in that, like, you know, you're picking up these values on the way up. And that's dominating your distortion. So we tried various ways of fixing this. We finally found one after quite a bit of experimentation. So it's to apply these random Fourier features. So there's this paper Tansik et al. 2020. which builds on some earlier ideas from Rahimi and Recht. So the premise of this Tansek et al. Paper is that stochastically trained neural networks are hypothesized to learn high frequency functions slowly and low frequency functions quickly. They learn everything eventually, okay, but they kind of learn the low frequency functions first and then the high frequency functions. Like if you're doing a simple regression or something, right? It's like, you know, a function of one variable. They kind of learn the low frequency functions a lot faster than the high frequency ones. And this is on some level explains how they can avoid overfitting, because you can run them and then you have this long window of the training period where they've kind of fitted the low frequency functions, not the high frequency functions yet. And so if you just stop it anywhere in that window, then you're good. Sometimes you need to learn a high frequency function, like in our case, there's no way around it. So in that case, Tansek et al. Suggest supplying the network with random Fourier features that give it high frequency functions of your data that you have created so that it can easily just pull them out and, you know, and use them. So this would look like in our setup is we modify the decoder. You do it with the encoder too, it doesn't really help, but it wouldn't hurt anything. But anyway, the decoder is where you really need it. So rather than giving the network U or U hat, the quantized version, you would take the input U and then pass it through all these sinusoids with like random frequencies. Okay. And now this MLP has access to like high frequency functions of U. And so it can, you know, just using straight like Fourier analysis, it can kind of construct this like steep step function that it needs more readily than it has to do it completely on its own. A bit sensitive to hyperparameters. Okay, so sorry, I've spent quite a bit of time like optimizing these things to get it to work, but it does help in that when you induce the random Fourier features, then you know, you're almost back on the curve. Right. So yeah, the classical story, you know, it had a good run, but perhaps of limited utility moving forward. I say this as someone, okay, who has spent a substantial portion of his life working on IID quadratic Gaussian source coding problems. Okay, so I think I have standing to say it's time to move on. So, so what does the future look like? You know, I don't know, but here are, you know, two simple examples to maybe start with: the Sawbridge and the ramp. Simple as they are, okay, they do meet these three goals. They explain the success of these nonlinear transforms, they quantify the gap to optimality, and they do point the way toward how to improve them. We have other processes we've looked at that I'm not talking about. So sinusoid with a random phase, you know, a circle. It's a circle in 2D. So that's a low dimensional manifold in a high dimensional space, right? It's a 1D set in 2 dimensions, right? So we looked at that one too. Neural networks actually have trouble compressing that one optimally, somewhat surprisingly, given how simple it is, et cetera. And various extensions here. Let me just mention 2 of them. I think network extensions are interesting. There are groups looking at applying neural networks to multi-terminal source coding, to multiple descriptions. We have Gaussian results for these that you can compare against, but I think, you know, some kind of low-D manifold would maybe make more sense moving forward. And then, you know, it'd be nice to generate some kind of more general theory. We've solved various examples. They're all one-off theorems. Okay, there's no like general framework for these things as of yet. So it would be nice to start work on that. And I will end there. Thank you.
Is there somebody else?
Yeah, no, you can go.
So I'm very much doing deep learning for a living, so, but I'm still going to take this. So my first claim is these are really pathological examples because it's very, very high frequency. It's an infinite dimensional system if you take Fourier transforms or any transform, right? So in that sense, if you restrict it, it's not going to do as well. And I felt in some cases you were giving side information to your neural network to do better. In both cases, so, and I'm not saying you don't need nonlinear transforms. You just so if you go back to read, it's Calderbank and some other people's papers, can't remember who's, where they claim that CNNs can be very well explained by transforms plus simple nonlinearity, right? Linear transforms and simple nonlinearity. Most images are not entirely like this. There's a lot of smoothness, there's some edges.
Okay, so there's a lot there.
My point is, you took some external examples is all I was saying.
Yeah, so
Maybe I'm wrong, maybe I'm wrong.
okay, I heard, let me try to tease out the questions that I heard there, the comments that I heard. So one was, I think I understood you to say that you thought this fault with the neural networks that we identified is not relevant in practice because it's sort of a degenerate example and maybe wouldn't generalize beyond this kind of like
this was great, not this, but the previous one.
The Sawbridge one?
Yeah.
Okay.
My argument is that, yeah. I mean, this is great, but didn't it feel like the neural network was given sufficient prior information about this kind of data set? Did I get
No. I mean, we just took Johannes's code and just ran it on Sawbridge realizations, and then that was that. We just did that. We didn't tweak it. I thought you were going to say in the other example with the random Fourier features, like, we're kind of hanging exactly what it needs. And Sawbridge, this was totally off the shelf. I can say that with a completely clear conscience. We just ran it, and the first time it just worked. Yeah. So I don't think here we were really providing it with side information per se. In this example,
all those instances.
Pick what up.
Gave it.
It learned to extract the U, exactly. So if you give it just one latent dimension, that latent dimension will be basically U or some invertible function of it. If you give it two, it'll usually turn off one of them. So it won't use it because it doesn't need to.
Right.
Although it will in some cases use it. So if the rate point that you're looking at is like log M, where M is not prime, and it'll like actually use both dimensions, and use one to like indicate whether U is like to the left or the right, and then the other one to indicate like a quarter. So it'll come up with some clever schemes to use both, but it doesn't need to. So sometimes you train it'll just use one, ignore the others. In other cases, it will come up with an optimal scheme that actually splits into two kind of independent latent variables.
So the second example basically shows there's a spectral limit even to these nonlinear systems, which is why you want to add those training further.
Yeah, it's just not learning. It needs to learn the left, basically, and it was learning the right. And so, yeah, I mean, I agree with the criticism that this feels a bit too handcrafted, unless maybe one proposes to just always do this, but it does fix the problem. And it's the only fix we really know of as of now.
Can you back to your curve where you show,
This one or the other process?
This one is good. So what's happening at below what is the blue curve below the lower bound?
Yeah. So this is a disagreement I've had with my co-authors on this. So the blue is not a curve. Okay, so the blue is just a trained neural network at different values of the Lagrange multiplier. So the blue is really this. And there's a dotted line connecting them for visual purposes, but it's not to imply that you can achieve anything here. You can achieve that and you can achieve that. And that's the assertion.
Yeah, so your converse is still true.
Sorry, yeah, the converse is still true.
We just couldn't go in between these.
So, okay, it's log scale is one thing. Also, maybe it's important to point out that the entropy distortion curve is not necessarily convex, because you can't time share if the encoder is deterministic anyway. With a rate distortion problem, you can always say like, okay, I'll use like 3/4 of my block length, I'll do this, and 1/4 I'll use that, and then you can interpolate between any 2 points. The way we formulate it is a one-shot entropy distortion problem. You can't time share. And so in fact, neither of these curves, even if you plot it not in a log scale, but just a linear scale, it's not a convex curve. In fact, I might even have like at the end from here. This is just mean squared error versus entropy for the Sawbridge, so you can see it. Not convex.
Okay, I think that's this sort of shape that's well known in compression.
Yeah. I didn't mean to imply this was like a new observation, but you can't connect the dots.
Yeah, just briefly, maybe I misheard you. At one point, I think before the ramp, you mentioned, or like as we were getting into that like the fact that the function space is a circle here plays some role. I was wondering, maybe I like missed the punchline here, but if you could just like say a couple sentences about like, is there something about the non-Euclidean nature of that function space that is screwing things up? Is there a connection there? Or?
Yeah. Let's see. Maybe it's maybe easier to describe in terms of the circle. It's like suppose the source was just like a point on the unit circle in 2D, right? So what you want is for the encoder to just look at the point on the circle and just encode like the phase. And the decoder and quantize it, and the decoder would then reproduce, point on the circle or maybe below the circle because it's like an MMSE thing, right? But if you think about the encoder's job, so it needs to read in a point on the circle and output the phase, right? Now the encoder transform needs to be a continuous function. You want it to be invertible, but you cannot map, like there's no map from R2 to R that maps the circle to the segment in a continuous and invertible way, right? You can start at one point, you map, you map 12 o'clock to 0, right? And then, as you're going around, you're right, you get to 1, and now what? You got to quickly come back to 0, right? So, so that phenomenon actually crops up also kind of with the ramp. It's another way of thinking about what's going on over here. Whereas the Sawbridge does not have that property. It's not returning back to itself, and so you don't have that same phenomenon cropping up.
Okay, thank you.
Okay, thank you, Aaron. Break, we're back at 3:25.